All right, hi guys. So we're going to finish up the 8.1.2 notes. So what you need to do right now is get the 8.1.2 guided notes out that we started in class. So this is what the first page looks like. And we're going to pick up right where we left off, which hopefully is right around 826. So we're going to talk about what happens when some of our factors of a polynomial have the factors themselves have these exponents here. So in this example right here, x minus 2 times x plus 5 squared. The factor x plus 5 is repeated because if I rewrote this as x plus 5 squared, I could think of this as x plus 5 times x plus 5. So we see this happening twice, and we call this a double root of the polynomial. So we call this a double root, and we're going to see what happens at a double root because it is different than what happens at something like x minus 2. So first we're going to answer what effect does this have on the graph. So again, you're going to need your graphing calculator handy every time we are in class. So right here I'm looking at, I've got it programmed in here, x plus 2, x minus 2 times x plus 5 squared. I'm just going to go to my standard viewing window. Nope, that is not the viewing window I wanted. All right, 1 second here. Okay, my bad. So I discovered that I could put backgrounds on my graphs and I forgot to change that. Okay, so now I'm looking at a clear view here of this graph. So what's happening at the double root? So like we learned in class, the roots of this are 2. So whatever makes this function equal 0, 2 would make this equal 0 because I would have 0 times something, and negative 5. So the roots, I'm just going to write that down. The roots are 2 and negative 5. The question is, what is happening at the double root where x equals negative 5? So what is happening there on the graph? I'm looking at negative 5 and I see it is touching the x-axis, which I should expect since I know negative 5 makes the y value 0, but it's touching it and then sort of bouncing off of it. And we call this bouncing off a deflection. So it's deflecting away from the x-axis. So what effect that this has on the graph is it deflects. I'm still going to write bounces off. I think that's just easier to understand. Bounces off. Technically, I would call that deflection. I'll just write deflects right there. So it's bouncing off, as opposed to the linear root. So this linear root of x minus 2 with the factor of x minus 2, which gives us the root of positive 2, it's just crossing straight through at positive 2. But the square on the factor of x plus 5 causes the graph to behave differently there. And I'm going to point your attention back to this example we did in class on the first page of these notes, which was we looked at all of these 4th degree polynomials here, and we saw that this one was also a 4th degree. But this one was unique because it only had 2 roots or 2 x-intercepts. Now these we can see are both double roots as well because of this squared right here on the factors. And we see this behavior again. It's deflecting off of the x-axis or bouncing off of the x-axis. And we're going to see that every single time we have these repeated factors, which is really cool because then you can predict basically what's going to happen on the graph at those intercepts. Okay, so what if it's not a double root? What if it's cubed? So what if it occurs 3 times? In this example, negative 0.1 times x plus 4 cubed. So if I wrote that out, it would be x plus 4 times x plus 4 times x plus 4. This doesn't change the fact that the root is negative 4. That's the root. So I know it's going to touch the x-axis at negative 4. But what is going to happen at the graph? So that's negative 0.1 times x minus 4, x plus 4 cubed. All right, let's see what happens at negative 4. So at negative 4, when I have a triple root or something cubed, it is not deflecting off of it. In fact, it's touching it and kind of like slithering through it. So it's kind of curving its way through that root. So I call it a squiggle. And someone else preferred to call it a slither. I don't care what you call it. I'll give you the formal term for it. So it squiggles through. That is called a point of inflection. So a point of inflection. And you don't need to know that term inflection. I just wanted to give you a term that's not as, random as squiggles. Okay, so when it's cubed here, and I want you to relate that back to what you know about the graph of x cubed, the parent function x cubed. So when I just graph x cubed, we can see and we're reminded, oh yeah, this graph is that we call an S shape. So it's kind of squiggling through that x-intercept of 0. So any cubic function, so now if I made that different but a cubic factor, like x minus 3 cubed, I'm going to see that same behavior no matter what. So it's always going to, that cubic factor is always going to kind of make it slither through the x-axis. So that's important for us to remember. So the cubic or third degree, we saw this slithering through. And this double root, we saw it, I'm just having quick visuals here, bouncing off. And that's going to be important to keep in mind. Then this next question here, what do I notice about the graphs of even degree functions versus odd degree functions? So again, let's look back up here. This is odd. And I want you guys to pay attention to what's happening at the ends of the graph. So basically where the arrows are. So that one is odd, and this one is 5th degree, so that one would be an odd degree as well. Now let's look at the even degree. So minimum degree of 2, here's what the ends are doing. And then a minimum degree of 4, and here are the ends. So I want you to think before I just tell you what the pattern is here, or what's the similarities I'm seeing between odd degrees, so 3, 5, 7, 9, or even degrees, 2, 4, 6, and 8. So what I'm hoping you guys are seeing is that the odd degree functions have ends that are doing opposite things. So an odd degree function, if it starts in the negatives, it's going to end in the positives. Or if it starts in the positives, it's going to end in the negatives. No matter where it starts, an odd degree function is going to end in that opposite direction. Then we have even functions, and with even functions, it's going to start and end in the same direction. So if it's starting down here in the negatives, it's going to deflect at some point and then end up back in the negatives. And same with 4th degree, and same with any other even degree. So with even degree functions, the ends behavior, the ends of the graph do the same thing, meaning they go in the same direction. Same direction. Odd degree functions, the ends I'll word this one differently, approach different directions. So that's going to be helpful to us when we start building these graphs. Odd degree functions, so cubic, so here's odd. They are all going to do this sort of thing. Or maybe it's like this. It might start up here and go down. No matter what, a odd degree function will start and end different places. Even functions, so here's an even. Same direction. It could be something like this, but they're still both going down. So even and odd. That's an important distinction to make between even and odd functions. All right, flip over the page. I'm going to show you just a kind of nice, quick way of talking about where a function is positive versus where a function is negative. So here we see these number lines with different bold parts. And the bold pieces of these number lines represent where the function is above the x-axis. So we can think about this as the x-axis, and I just haven't drawn the vertical y-axis. This is just a way of talking about where is the function over it, above it, and where is the function negative, below the x-axis. So in this, the bold pieces represent where the function is positive, meaning if it's bold from -3 to 1, but it's not bold on the outside of those 2 points, then and -3, -1, and 4, these are the zeros or the x-intercepts of the graph. So if -3 and -1 are x-intercepts, and it's bold between them. That means it's crossing through the x-axis there, and it's above, the function would be positive there. So I'm just kind of sketching what these bold pieces of the number line mean. So since it's not bold before -3, that means it's going to continue in the negative direction for infinitely. Between -1 and 4, it is not bold. So that would be a negative piece of the graph. So it's under the x-axis. And then I see it's bold again after 4. So it's going to be crossing through and staying positive. So this is just, these number lines are kind of like a short, quick way of showing you visually where a graph is positive and where a graph is negative. So I'm going to look at B again, and then we'll jump down to example 29. So here we've got, this one's a little different. So my x-intercepts are -5, 0, and 2. So, but it's all bold between all 3 of these x-intercepts, and then not bold here. So the fact that it's not bold here tells me that my function is going to start negative, and then it's going to become positive, but it's going to touch the x-axis at 0, and then it's going to stay positive again after it. So that means at 0, I am going to have this point of inflection, or that bouncing off. So that kind of helps me fill in what the other pieces of this graph may look like. It's negative, and then it's positive, bouncing off at the root of 0. And then after 2, it's negative again. So that this piece right here is not meant to be bold. If you look really closely, it's kind of like not as bold as this, but more bold than this. So it's meant to be negative right there. So that means it's going to cross back through and remain negative. So again, these number lines are just a quick visual representation of where a function might be even or where it might be odd. So let's go in the opposite direction then. So if I give you the graph, this graph we looked at on the last page of notes, but I will plug it back in really fast so we can take a quick look at it. So if I'm plugging in x minus 2 times x plus 5 squared. Okay. All right, so here's my graph. Again, we looked at this. We saw the point of deflection right here at -5 because it's a double root. And then my other root of 2 just crosses right through. All I'm really paying attention to, these are just where, these are visual representations of where the function is positive and negative. First, I'm going to graph my roots. So this one has a root at 2 and -5. So what is this function doing at before and after -5? It's actually negative before and after -5. So that means it's just coming up and touching -5 right here. I'm actually not going to sketch. I don't want to put the emphasis on sketching the graph, more so as building the number line. So it's negative, so I'm not going to make this bold. It's still negative here, so I'm not going to make that bold. And then it crosses through the x-axis and is positive after 2. So the only piece of this number line that would be bold is right here after 2. Because that's the only place that this function is positive, is for all of the x values after 2. Before that, it's always negative, except for here where it actually equals 0. We'll do one more quick one just to kind of hopefully solidify your understanding of this. Again, these number lines are just a quick visual representation of where a function is positive, meaning above the x-axis, versus where the function is negative or below the x-axis. All right, so here, okay. So here's the graph of this one. This is a third-degree polynomial. I see 3 linear factors, so third-degree polynomial. And my zeros, or my roots, are at wherever this whole thing would equal 0, which would be when x is +2, -2, or +3. So those are where it's touching the x-axis. Now I want to just shade based on where this graph is positive. So left of -2 right here, it's negative. So nothing will be shaded to the left of -2. It is positive right here. I can see it's positive between -2 and +2. So I would shade right here between -2 and +2. Then it's negative just for a little bit between 2 and 3. And then positive again after 3. So this shaded region right here between -2 and 2, and then after 3. Again, just a quick way to represent where a function is positive or negative. So now we have the tools. This is kind of like the final goal of this lesson is, can you look at this and sketch an accurate graph, or sketch the behavior of this graph just based on its factored form. So there's a couple things we're looking for. This problem right here, I know you guys it's easy to mindlessly write down what I'm writing down when you're taking these video notes. Please stop and think about these, because this is an important piece, kind of wrapping up the entire lesson. We want to go from factored form of a polynomial to a sketch of the graph. And there's a few things we need to keep in mind. What is the degree? And what are the roots? And where is it going to start and end? And the degree is going to help us determine that, because remember, we saw that odd degree functions started and ended in opposite places. Even degree started and ended in the same place. So what degree is this graph? So I see 3 x's here all being multiplied together. So this is a 3rd degree polynomial. It's odd. And then I'm going to graph the roots, because I know that the graph is going to touch the x-axis at my roots. I have 3 roots in this one. The roots are the x values that would make this whole thing equal 0. So that would be when x is 0. X plus 1 gives me the root of -1. And x minus 3 would give me the root of +3. So next I need to think about what the graph is doing there. So it's right here. None of these are double roots or triple roots. So these are all just linear roots, which means it's going to just cross through the x-axis there. And then the next thing I need to remember is that as a 3rd degree polynomial, it's going to start and end in a different place. So think about the parent graph of y equals x cubed. Again, this graph is going to help us determine where this 3rd degree polynomial starts and ends. So in the cubic function x cubed, the parent graph starts in the negatives and ends in the positives. So typically that's what this one would do. However, this negative coefficient is going to have the effect of reflecting that over the x-axis. So it's actually going to start in the positives. So my graph right here is going to start up here and end down here. So it's going to do this. It's going to cross through, and cross through again. So this is what I know where my roots are, and I know what the function is doing at those roots. So crossing through. And if I wanted to check this on the graph, I could easily do that. This isn't going to be a perfect graph of that, but it's going to at least show me what's happening at the roots and where it starts and ends. So here's my graph. And there I see I'm not totally accurate with y values, but I can see it starts up here. It's crossing through at -1 and 0, and then back down. So right now, if you've been hanging with me these first couple of lessons, what you're able to do now, which I think is really cool, is graph a polynomial without a graphing calculator, just based on what the equation tells us about it. Let's look at B. So this one, I have a double root at 1. So I'm going to put 1. I've got a linear root, meaning it's just going to cross right through at -2. And another root would be at +4. Okay, this is a 4th degree polynomial. There's only 3 roots, but this one is a double root, and then these 2 as well. So 1, 2, 3, 4. This is 4th degree. It means my ends are going to do the same thing. My leading coefficient, as opposed to this example, which was negative, this leading coefficient is just +1. So I'm going to think back to, again, the graphs from the front of this lesson right here. So here's a 4th degree polynomial. When they have positive exponent or positive coefficients, they start and end in the positives. So that tells me this graph is going to start up here and end up here. And then I need to figure out what's happening at each of these roots. So at -2, which is just a linear root, it's just going to cross right through it. Then at 1, where I had a double root, it's going to bounce off of it down here. So it's not going to cross through, it's going to bounce off. And then at 4, it's going to cross through. So that is the behavior. And again, I can plug that in and check it, and that will confirm that this is an accurate representation of where the roots are and what's happening at those roots. All right, so if you're feeling like you've got the hang of this, well, actually, I was gonna have you pause this video and try this one on your own. This triple root, which you can do if you wanna try and then see if you're on track. This one right here is a little different, and people always wonder, what do I put, how do I graph that? If you remember back, we looked at, on the last page, this cubic root here, this factor made the graph what I call squiggle through. So we're gonna have to replicate that here. The total degree of this function, I have a triple root right here, plus this one linear root. So this is a fourth degree, degree 4. Again, the ends are gonna do the same thing. This has a positive coefficient, so both ends are gonna be positive. So I'm just drawing those arrows to remind me it's gonna start up and end up. All right, so my roots are +4 and -2. Now, at -2, I have this third degree, which means it's going to, like I said, kind of squiggle through, or there's going to be a point of inflection. So when you're sketching that, you would just come down to the left of it and then try your best to get that little curve or slithering through that 0 of -2. And then it's going to go, x minus 4 is just a linear root, so I know it's just going to cross through that one. So that is what a sketch of this graph would look like. All right, so like I said, this final problem, number 830, is kind of like my goal for you guys, that you guys could look at a factored form of a polynomial and sketch a graph of that. So I'll stop here, and I will see you next time. Have a great day.